Alright, so we've got 1.2 functions and their properties. So I'm going to have some definitions to start with. A function from a set D to a set R is a rule that assigns to every element in D a unique element in R. Okay, D being domain of the function, and R being the range of the function. Notice for function notation, we would have something like y is equal to f of x, and I'm just going to put how it is read over here. Okay, just so that you're familiar with that when you hear me say that, that's what I'm talking about. Functions can be used as mapping of the elements of the domain onto elements of the range. So we could have something like, I'm going to draw, do an X and a Y for input and output, and then I'm going to do another one over here. Okay, and remember, for a mapping diagram to be correct, you have to write input and output, and then we're going to have all the values down here. X2, X1, X3, X4. Remember, these are just representing numbers. Y2, Y1, Y3. Okay, and then over here on the other one, I'll set them up and then I'll draw the little lines. X2, X1, X3, X4. Y2, Y1, Y4, Y3. All right, so this would be, if we have this scenario, something like this. Okay. And on the other one, whoa, undo. Always helps to pay attention when the eraser pops up. X2 to Y2, X1 to Y1. X1 is also going to go to Y3, or oops. Okay, X3 is going to go to Y3. Or well, here, I can actually draw it this way. And X4 to Y4. Okay, so we want to know which one is a function. So before I write below each of them which one is a function, I'm going to do a little refresher here on how to know if it's a function or not, just in case we don't remember. To be a function, each input must have exactly one output. Okay, so looking at the two above, one of them is a function and one is not. So take a second and think about, look over that, okay? Are there any inputs that have two outputs? Okay, or more than one output? Okay, hopefully you see that here in the second one. So the second one is not a function, okay, because of the x1 having two outputs that come from it. Okay, the first one is a function because each input only has one output. I'll leave that there for a second. All right. The graph of a function, it must pass the vertical line test to determine if something is a function. Okay, so that implies holding your pencil up and down like that. Okay, and dragging it left to right. If at any point it hits twice, it is not a function. Okay, so the vertical line test a graph in the xy plane defines y as a function of x if and only if no vertical line intersects the graph in more than one spot. Or I guess I should say point to be a little more accurate. All right, so this next thing, I'm not going to actually do any examples of it in the notes, just because I'd rather talk about it in class, but domain and range is kind of the next big thing. So domain is all possible x values that make the function true. Okay, range are all possible y values, okay, that it takes on in the graph. Okay, typically domain I require you to actually know. Range I do a little bit more, like just look at a graph and tell me what it is. There are ways to find it, so we will kind of talk about that, but I'm not going to spend a lot of time with that right now. Excuse me. All right, so the next thing here is continuity. All right, so with continuity, okay, it's kind of the next big topic. So on a graph, a function is continuous at a point if the function does not come apart at the point. Okay, so you need to draw 5 little mini graphs, okay, with enough room to write about, well, enough room to write about 2 lines underneath of them. So I'm going to go ahead and set these up here. Trying to make them all relatively the same since I tend to change sizes as I go across. All right, good enough. Need like a copy paste function. All right, so I'm going to draw here these graphs. Okay, they don't have to be perfect, and I'll go underneath afterwards and write exactly what you need to know. Okay, so something like that. This one, you're going to have a little break here. Okay, and then above the break, go up a little bit and have a filled in circle. Next one, we're just going to have that little hole in it. The next one, have a hole, jump up above it, have a filled in, and finish it. And then this one over here is the most different. Whoa. Don't know what just happened. What is going on? I don't understand. Okay, there we go. Sorry, I was a little frantic. Don't know what just happened. Okay, so I'm going to go through and write what kind of either continuity or discontinuity each of these has, and then I'll explain why on each one after that, just so I don't have to keep changing back and forth with colors. So this first one is continuous at all x values. Okay, so CONT is continuous. Okay, both this one and the next one are removable discontinuity. This fourth one is a jump discontinuity. And this final one is an infinite discontinuity. Okay, we just need to rewrite this because that just looks bad. Okay, infinite discontinuity. So now underneath each of these, I'll write the reasoning. So the first one is continuous at all x values because there is no break. Okay, there's no empty spots. It is one continuous thing. You put your pencil down and you draw the whole thing without stopping. Okay, essentially a way to think about it. The next two, you'll notice they both have this little empty space in them. Okay, and that's what we call a hole. So this one has a hole and this one has a hole. Okay, this one here looks like it's got something that's filling it in at that value, but because there is an empty spot, that's why it's the removable discontinuity. So the jump discontinuity is, well, as you can see, it literally jumps up and continues. So this one is more than just a hole at the point. Okay, and we do this in relation to the x values, if you're wondering how we decide this. And then lastly, for infinite discontinuity, it is not removable. Okay, so there's no holes, no gaps, nothing. Okay, it just, the graphs just do not touch. And you'll notice at 0 there, they don't ever actually cross that y-axis there. Sorry, too far. All right, the next thing we have, you're going to need 4 graphs again, but it's going to be increasing and decreasing functions. Okay, so we're going to draw 4 graphs this time instead of 5. So I'm going to work my way across here with these. Okay, good enough. This line doesn't look straight, so I'm going to fix it. Good enough. Okay. So again, I'm going to draw the graphs and then we'll talk about each one of them. And again, it doesn't have to be perfect. Just something like that. Like that. Straight across. And this is a weird one. What just happened? That was really weird. All right, straight across. Okay, and this point, -2 and 2. All right, so you're just going to have one word underneath the first 3, and then we're going to have 3 little line things underneath the last one. All right, so this first one, function starts low and is getting higher, so that's going to be an increasing function. Second one starts high, goes low, so it's going to be decreasing. The third one, it stays the same all the way across, so we can say it's staying constant. And then the last one, okay, we can't see the whole graph, okay, it's stopping there, we can't see it, it does keep going. So what we would say with something like this is that you're decreasing from -infinity to -2. Okay, and we bracket it off because it's a closed circle there. It's constant from -2 to 2, and again, they're bracketed off for the same reason. And then lastly, after that, it goes up, so it's increasing from 2 to infinity. And remember, with the infinities, they do have the parentheses on each end of them. So give a second to make sure you get all of those copied down. Slide this up just a little bit, start writing some more definitions. Still underneath this increasing and decreasing stuff. For me on my paper, it's about 9 lines, but most of y'all write smaller than me, so it probably will be about 6 for you guys. Fun colors. Dark purple. All right. A function f is increasing on an interval if for any 2 points in the interval a positive change in x results in a positive change in f of x And if this stuff is like looking really confusing to you, once we do examples, it'll make a lot more sense. I'm trying to give you some visuals here, and then also it in words to hopefully help it make a little bit more sense until we get back in and doing examples with it. A function f is decreasing on an interval if for any 2 points in the interval a positive change in x results in a negative change in f of x and then the last one of these, a function f is constant on an interval if for any 2 points in the interval a positive change in x results in 0 change in f of x. Okay, so that's again just in words what all of that means. All right, so we have 4 more like major topics here. About this stuff. So I know this is a really long section. And it's a lot, but it all kind of just ties together. So let's go ahead and pick up here with boundedness. Okay, so I need 4 graphs drawn again. And leave about, you're going to need about 2 lines to write below them. Okay. So just leave a little bit of space. Again, the graphs don't have to be real big or anything special. All right, so this one, a little bit like that. Next one. This one. And this last one, notice I'm putting little dots on it. Oh, wait. Ah! Okay, I guess I get to do it again. No, stop that. Okay. There we go. All right, so in regards to these, okay, we're looking at if it's bounded above or below or not, or if it's just completely bounded. So a function could be just bounded above, could be just bounded below, or it could be completely bounded. Okay, so for the first one, okay, there is no ending points on it, okay, and it's not all connected together. So this one we're going to say is not bounded above, Okay, and I use BDD for bounded. Okay, it's a shortened word because I get tired of writing it. So not bounded above, and it's not bounded below. Okay, on this next one, if we look at it, okay, it keeps going up to infinity, okay, in the y direction, it's going up to infinity, so it's not bounded above. But at the bottom, you notice that it hits, it turns around, it comes back down, and it hits and turns around again, okay? It can't go lower than that based on the direction this graph is going, and because of that, we can say that it is bounded below. Okay, so something like this, these graphs are a little extreme, but something like a parabola, the parent function of a parabola, okay, would be bounded below, but not bounded above. So just to kind of help you visualize something that you're a little more familiar with. This third one, okay, at the top, okay, it stops. It can't go any higher than it is in this graph. So in this case, it's bounded above. Okay, but to the bottom, notice it can go all the way down to negative infinity in the y direction, so it is not bounded below. And then the last one, okay, looking at it, you might be looking at it and thinking, well, maybe you could justify it being bounded above without really knowing what's going on here. Because of these little dots on it, okay, that is telling you that that is bounded. It is not existing anywhere outside of that. So we don't have to talk about above and below. We can purely just say that this one is bounded. Okay, and something to note, we can bound any function on an interval. Okay, meaning we can decide that from -2 to 2, that's what we're going to deal with, and we can bound it there. Okay, you can't bound something at infinity because it keeps going forever, so just keep that in mind. So we can bound it like you see in the fourth graph. That could have been a function that would have kept going, okay, but we chose to bind it, I don't know how you want to say that, okay, not an English teacher, remember that. We're going to bound it, okay, between those 2 points there, and so that's how we would do that on an interval. All right, sorry if there's just a little glitch there, I had a minor problem. So the next thing is the local and absolute extrema. So a local maximum, okay, a lot of times you'll just hear me say local max of a function is the function f, is the value f of c that is greater than or equal to all range values of f on some open interval containing c if f of c is greater than or equal to all range values of f, then f of c is the maximum or absolute max value of f Okay, again, these will make a lot more sense when you see them in examples. So if you're like sitting here super confused, please understand that it will make sense more with examples. This is a section that just takes a lot longer. So local minimum of a function, f is the value f of c that is less than or equal to all range values of f on some open interval containing c if f of c is less than or equal to all range values of f, then f of c is the minimum or absolute minimum value of f. And local extrema are also called relative extrema. Okay, just another name for them. All right, so the next major thing is symmetry. And so we're going to talk about it with respect to the y-axis, x-axis, and the origin. For me, it literally took up a whole page, so just a heads up there. So first, with respect to, okay, WRT means with respect to, in case you see that written. So with respect to the y-axis first, so for example, we're going to use f of x is equal to x squared. And so I'm going to show each of these things graphically, numerically, and algebraically. So graphically, numerically, and algebraically. So graphically, I'm just going to have a parabola, close enough, and it's going to have the point xy and negative xy. Then numerically, we've got x, f of x, -3, -2, -1, 1, 2, and 3. And then f of x would be 9, 4, 1, 1, 4, 9. Okay, this you just get from plugging in that value for x in x squared. So when you square each of these x values, what value you get out. And then algebraically, for all x in the domain, remember the upside down A is for all, of f, f of negative x is equal to f of x. Something to note, if a function has this property, it is an even function. Okay, so just keep that in mind. Okay, that's something that you need to know. Actually, here, I'll just highlight it. Okay. Oh, that was fun. All right, so then the next one we would do with respect to the x-axis. And for that example, I'm going to be dealing with x is equal to y squared. Okay, and that has to do with the type of problem I'm dealing with here. If you need to pause to get the stuff that I wrote down before, I would do that because I'm going to slide it up here. All right, so again, we're going to do graphically, numerically, I don't know what that is, and algebraically. All right, so graphically, what color did I use up there? Red. I already forgot. All right, so we're going to have kind of a sideways parabola here. Oh, that. All right, there we go. Close enough. So we've got the point xy and the point x negative y. So numerically, we've got x and y, 9, 4, 1, 1, 4, 9, means y is negative 3, negative 2, negative 1, 1, 2, oops, these aren't lining up, so that's probably confusing. Negative 1, 1, 2, and 3. Okay, and that's just if you plug in these values for x, what do you get for y? Okay, you'd have to take the square root of x to get y. So that's where that's coming from. Algebraically, graphs with this, symmetry are not functions. Okay, why are they not functions? Because it does not pass the vertical line test, but x negative y is on the graph when xy is on the graph. That was weird. All right, so I'll leave that for a second and then you may want to pause it. But with respect to the origin is next. So with this one, we're going to use f of x is equal to x cubed. Okay, this one is going to be a function. So again, you may want to pause here real quick if you don't have all that down. All right, so I'm going to do, again, graphically, numerically, and algebraically. So with my graph, I've got something like that. So it has the point xy and the point negative x, negative y. Numerically, got negative 3, negative 2, negative 1, 1, 2, and 3. Plugging those in for x, okay, I get out negative 27, negative 8, negative 1, 1, 8, and 27. Algebraically, then we say for all, remember that's the upside down A is, x in the domain of f of negative x is equal to negative f of x. And then another thing to note with this property, a function is an odd function all right. So I would mark all of that down. All right, so the final thing for this section, I know this is like insanely long, is called asymptotes. Okay, it's not spelled quite like you would think it would be spelled. Like it doesn't sound like there's a P in it, but there is. Okay, it's a weird word, but just know that it exists. So the line y is equal to b is a horizontal asymptote of the graph of a function y is equal to f of x if f of x approaches a limit of b as x approaches positive infinity or negative infinity. Okay, I'm going to teach you limit notation. I don't really think that our book uses it a whole lot, but you will need this if you go on past this class, and we might briefly use it. I just think it makes life a little easier. But we say the limit as x approaches negative infinity, okay, that's how you say that, of f of x is equal to b, or the limit as x approaches infinity of f of x is equal to b. Okay, I think I may have briefly mentioned limit notation to you last year, but if you see it, that's why. The line x is equal to a is a vertical asymptote of the graph of a function y is equal to f of x if f of x approaches a limit of positive infinity or negative infinity as x approaches a from either direction. So in limit notation for this one, I guess I should have written this as limit notation. Limit as x approaches a from, okay, the negative sign in the superscript means from the left of f of x is equal to positive or negative infinity, or the limit as x approaches a from the right of f of x, okay, the positive superscript means from the right, is equal to positive or negative infinity. For vertical asymptotes, consider the denominator and where it is equal to 0, x equals whatever. Okay, vertical is probably the easier one because you're really just looking at the bottom of a fraction and saying, where's that equal to 0? That's all you have to do for vertical. For horizontal, asymptotes, we look at the highest power of the variables, top and bottom, and it is written as y is equal to blah blah blah. So something to note is, what is going on? Asymptotes are written as an equation of a line. Okay, I have a fun way to remember the horizontal asymptotes. Okay, and I even have a little poem that I have to remember to get it out, so remind me when I get back. It's Bobo, Botno, Bosco, and he's a clown. Okay, so I'm just going to give you the little heads up. It's fun, but anyways, just be aware that that's coming down the pipeline, and if you memorize it, I give you extra credit on your test. All right, so Bobo, bigger on bottom is 0. Bosco, both the same. The answer is the coefficient. And lastly, Botno, bigger on top. There is no horizontal asymptote. And the last thing under here, actually I had forgotten about, just in general, is called end behavior. Okay, so this is essentially what happens as we go really, really far away from 0. So horizontal asymptotes, okay, and I typically will abbreviate horizontal asymptotes as HA and vertical asymptotes as VA. So if you see that, just make a note of that. So horizontal asymptotes help to show one kind of end behavior as functions go to one end of the x-axis or the other. Okay, so I know that's a lot of notes and a lot of material, and you probably are sitting there pretty confused if I had to guess, just off of hearing this information. But know that once you see examples and stuff, this stuff is actually, to me, kind of fun, and it's really not hard. So just be aware of that. If you seem confused, don't be like, oh my goodness, I need to go drop this class because it's so confusing. It's really not, and you'll be okay. So anyways, that should be all for the notes for this section.